building the model. Okay, so this is where we need to talk a bit more in depth of what we're actually going to build. So the model for this is a classification model. Now there is like hundreds of different classification models we can use that are pre-made in TensorFlow. And so far what we've done with that linear classifier is that's a pre-made model that we kind of just feed a little bit of information to and it just works for us. Now here we have two kind of main choices that we can use for this kind of classification task that are pre-built in TensorFlow. We have a DNN classifier, which stands for a deep neural network, which we've talked about very vaguely, very briefly, and we have a linear classifier. Now, a linear classifier works very similarly to linear regression, except it does classification rather than regression, so we get actually numeric value, or we get, the labels, like probability of being a specific label rather than a numeric value. But in this instance, we're actually going to go with deep neural network. Now that's simply because TensorFlow on their website, like all of this is kind of building off of the TensorFlow website. Just all of the code is very similar, and I've just added my own spin and explained things very in depth. They recommend using that. Deep neural network for this is a better kind of choice. But typically when you're creating machine learning apps, you'll mess around with different models and kind of tweak them. And you'll notice that it's not that difficult to change models because most of the work comes from loading and kind of pre-processing our data. Okay, so what we need to do is build a deep neural network with two hidden layers with 30 nodes and 10 hidden nodes each. Now I'm going to draw out the architecture of this neural network in just 1 second, but I want to show you what we've done here. So we said classifier equals tf.estimator. So this estimator module just stores a bunch of pre-made models from TensorFlow. So in this case, DNN classifier is one of those. What we need to do is pass our feature columns just like we did to our linear classifier. And now we need to define the hidden units. Now, hidden units is essentially us building the architecture of the neural network. So like you saw before, we had an input layer, we had some like middle layers called our hidden layers in a neural network, and then we had our output layer. I'm going to explain neural networks in the next module, so this will all kind of click and make sense. For now, we've arbitrarily decided 30 nodes in the first hidden layer, 10 in the second, and the number of classes is going to be 3. Now, that's something that we need to decide. We know there's 3 classes for the flowers, so that's what we've defined. Okay, so let's copy this in. Go back to the other page here, and that is now our model. And now it is time to talk about how we can actually train the model, which is coming down here. Okay, so I'm going to copy this, I'm going to paste it over here, and let's just dig through this because this is a bit more of a complicated piece of code than we usually used to working with. I'm also going to remove these comments just to clean things up in here. So we've defined the classifier, which is a deep neural network classifier. We have our feature columns, hidden units, classes. Now to train the classifier. So we have this input function here. This input function is different than the one we created previously. Remember when the one we had previously was like make input, whatever function, I won't continue typing, and then inside it defined another function, and it actually returned that function from this function. I know, complicated. If you're not a Python kind of pro, I don't expect that to make perfect sense. But here we just have a function, right? We're not returning a function from another function, it's just one function. So when we want to use this to train our model, what we do is create something called a lambda. Now, a lambda is an anonymous function that can be defined in one line. When you write lambda, what that means is essentially this is a function. So this is a function, and whatever's after the colon is what this function does. Now, this is a one-line function. So like if I create a lambda here, right, and I say lambda print hi, and I said x equals lambda, and I called x like that, this works. This is a valid line of syntax. Actually, I want to make sure that I'm not just like messing with you when I say that and that this is actually correct. Okay, so sorry, I just accidentally trained the model, so I just commented that out. But you can see we're printing hi, right? At the bottom of the screen, I know it's kind of small, but it does say hi. That's how this works, okay? So this is a cool thing. If you haven't seen this in Python before, that's what a lambda does. Allows you to define a function in one line. Now, the thing that's great about this is that we can say like, x equals lambda, and here put another function, which is exactly what we've done with this print function. And that means when we call x, it will, execute this function, which will just execute the other function. So it's kind of like a chain, right? You call x is a function, and inside that function, it does another function, right? It's just like calling a function from inside a function. So what is lambda doing here? Well, since we need the actual function object, what we do is we define a function that returns to us a function. So this actually just like it calls this function when you put this here. Now there's no, it's very difficult to explain this if you don't really understand the concept of lambdas and you don't understand the input functions. But just know we are doing this because of the fact that we didn't embed another function and return the function object. If we had done that, input function that we had created before where we had the interior function, then we wouldn't need to do this, because what would happen is we would return the input function, right? Like that, which means when we passed it into here, it could just call that directly. It didn't need to have a lambda. Whereas here though, since we need to just put a lambda, we need to define what this is, and then this works. That's just, there's no other way to really explain this. So yeah, what we do is we create this input function. So we have train y, and we have training equals true. And then we do steps equals 5,000. So this is similar to an epoch, except this is just defining a set amount of steps we're going to go through. So rather than saying like we'll go through the data set 10 times, we're just going to say we'll go through the data set until we've hit 5,000 numbers, like 5,000 things that have been looked at. So that's what this does with that train. Now let's run this and just look at the training output from our model. It gives us some like things here. We can kind of see how this is working. Notice that if I can stop here for a second, it tells us the current step. It tells us the loss. The lower this number, the better. And then it tells us global steps per second. So how many steps we're completing per second. Now at the end here, we get final step loss of 39, which is pretty high, which means this is pretty bad, but that's fine. This is kind of just our first test at training a neural network. So this is just giving us output while it's training to kind of say what's happening. Now, in our case, we don't really care because this is a very small model. When you're training models that are massive and take terabytes of data, you kind of care about the progress of them. So that's when you would use kind of that output, right? And you would actually look at that. Okay, so now that we've trained the model, let's actually do an evaluation on the model. So we're just going to say classifier.evaluate. And what we're going to do is a very similar thing to what we've done here, is just pass this input function, right? Like here with a lambda once again, and reason we add the lambda when we don't have this like double function going on, like a nested function, we need the lambda. And then in here, what we do is rather than passing train and train y, we're going to pass test, I believe, and then I think I just called it test y. Okay, and then for training, obviously this is false, so we can just set that false like that. I'm just going to look at the other screen to make sure I didn't mess this up because, again, I don't remember the syntax. Yeah, so classifier.evaluate test y looks good to me. We'll take this print statement just so we get a nice output for our accuracy. Okay, so let's look at this. Again, we're going to have to wait for this to train, but I will show you a way that we don't need to wait for this to train every time in 1 second, and I'll be right back. Okay, so what I'm actually going to do, and I've just kind of paused like the execution of this code, is throw this in the next block under, because the nice thing about Google Collaboratory is that I can run this block of code, right? I can train all this stuff, which is what I'll run now while we're talking, just so it happens. And then I can have another code block kind of below it, which I have here. And it doesn't matter, I don't need to rerun that block every time I change something here. So if I change something in any lower blocks, I don't need to change the upper block, which means I don't need to wait for this to train every time I want to do an evaluation on it. Anyways, so we've done this, we've got test y. I just need to change this instead of eval result. Actually, I need to say eval underscore result equals classifier.evaluate so that we can actually store this somewhere and get the answer. And now we'll print this, and notice this happens much, much faster. We get a test accuracy of 80%. So if I were to retrain the model, chances are this accuracy would change, again, because of the order in which we're seeing different flowers. But this is pretty decent considering we don't have that much test data, and we don't really know what we're doing, right? We're kind of just messing around and experimenting for right now. So to get 80% is pretty good. Okay, so actually, what am I doing? We need to go back now and do predictions. So how am I going to predict this for specific flowers? So let's go back to our core learning algorithms, and let's go to predictions. Now, I've written a script already just to save a bit of time that allows us to do a prediction on any given flower. So what I'm going to do is create a new block down here, code block, and copy this function in. Now we're going to digest this and kind of go through this on our own to make sure this makes sense. But what this little script does is allow the user to type in some numbers, so the septal length, width, and I guess petal length and width, and then it will spit out to you what the predicted class of that flower is. So we could do a prediction on every single one of our data points like we did previously, and we already know how to do that. I showed you that with linear regression. But here I just wanted to do it on one entry. So what do? So I start by creating an input function. It's very basic. We have batch size 256. All we do is we give some features, and we create a data set from those features that's a dict, and then dot batch and the batch size. So what this is doing is, notice we don't give any y value, right? We don't give any labels. The reason we don't do that is because when we're making a prediction, we don't know the label, right? Like we actually want the model to give us the answer. So here I wrote down the features. I created a predict dictionary just because I'm going to add things to it. And then I just prompted here with a print statement, please type numeric values as prompted. So for feature and feature, valid equals true, while valid, val equals input feature colon. So this just means what we're going to do is for each feature, we're going to wait to get some valid response. Once we get some valid response, what we're going to do is add that to our dictionary. So we're going to say predict feature. So whatever that feature was, so septal length, septal width, petal length, or petal width is equal to a list that has, in this instance, whatever that value was. Now, the reason we need to do this is because, again, the predict method from TensorFlow works on predicting for multiple things, not just one value. So even if we only have one value we want to predict for, we need to put it inside of a list because it's expecting the fact that we will probably have more than one value in which we would have multiple values in the list, right? Each representing a different row or a new flower to make a prediction for. Okay. Now we say predictions equals classifier.predict, and then in this case we have input function lambda input function predict, which is this input function up here. And then we say for prediction dictionaries, because remember every prediction comes back as a dictionary. In predictions, we'll say the class ID is equal to whatever the class IDs of the prediction dictionary at 0. And these are simply, I don't know exactly how to explain this. We'll look at it in a second, and I'll go through that. And then we have the probability is equal to the prediction dictionary probabilities of class ID. Okay. Then we're going to say print prediction is. We're going to do this weird format thing. I just stole this from TensorFlow. And it's going to be the species at the class ID and then 100 times probability, which will give us actual integer value. We're going to digest this, but let's run this right now and have a look. So please type numeric values as prompted. Septal length, let's type like 2.4. Septal width 2.6, petal width, let's just say that's like 6.5, and yeah, petal width like 6.3. Okay, so then it calls this and it says prediction is Virginica. I guess that's the class we're going with, and it says that's an 83 or 86.3% chance that that is the prediction. So yeah, that is how that works. So that's what this does. I wanted to give a little script. I wrote most of this. I mean, I stole some of this from TensorFlow, but just to show you how we can actually predict on one value. So let's look at these prediction dictionary because I just want to show you what one of them actually is. So I'm going to say print pred underscore dict, and then this will allow me to actually walk through what class IDs are, probabilities are, and how I've kind of done this. So let's run this septal length. Okay, let's just go like 1.4, 2.3. I don't know what these values are going to end up being. And we get prediction is same one with 77.1%, which makes sense because these values are similar, kind of in difference to what I did before. Okay, so this is the dictionary. So let's look for what we were looking for. So probabilities, notice we get 3 probabilities, one for each of the different classes. So we can actually say what, the percentages for every single one of the predictions. Then what we have is class IDs. Now class IDs, what this does is tell us what class ID it predicts is actually the flower, right? So here it says 2, which means that this probability at 77%, that's at index 2 in this array, right? So that's why this value is 2. So it's saying that that class is 2. It thinks it's class 2. Like that's whatever was encoded in our system is 2, and that's how that works. So that's how I know which one to print out, is because this tells me it's class 2. And I know from making this list all the way back up here, if I could get rid of this output, where is it? When I say species, that number 2 is Virginica, or I guess that's how you say it. So that is what the classification is, or that's what the prediction is. So that's how I do that, and that's how that works. Okay, so I think that is pretty much it for actually classification. So that was pretty basic. I'm going to go and see if there's anything else that I did for classification in here. Okay, so here I just put some examples. So here's some example input and expected classes. So you guys could try to do these if you want. So for example, this one, septal length, septal width. So for 5.1, 3.3, 1.7, and 0.5, the output should be Setosa. For 5.9, 3.0, 4.2, 1.5, it should be this one. And then obviously this for this, just so you guys can mess with them if you want. But that's pretty much it for classification. And now on to clustering.